Hi, I'm Matthias Grundmann, research scientist at Google. I'm going to talk today about live perception for mobile and web. What do we mean by live perception? Basically, any kind of machine learning that happens in the viewfinder. That is, on device, in real time, and with low latency. There are an abundance of applications. For example, virtual makeup and AR glass try-on, self-expression effects like those present in Duo and Snapchat, and smart framing solutions like you can find on the Portal or Nest devices. There are clear benefits of live perception because all computation happens on device with no connection to the internet. We're also not sending any data up to servers, making our solutions inherently privacy conscious. And because results in the viewfinder are immediate, it enables you use cases like creating in the viewfinder as you've seen in YouTube or in TikTok. Now, this sounds great, but what are the technical challenges? Well, for one, any kind of machine learning inference needs to be completed in 20 milliseconds or less because you usually want to run additional processing steps like rendering on top of it. And that means you are constrained to low capacity networks. Classical approaches like distilling a large server model tend to lead to poor results. So you need to design your models with live perception in mind. I'm going to share with you 5 core recipes that we found to be quite successful in that domain. Now, it's not just the ML models, it's also critical infrastructure. And they both go hand in hand. Live perception requires cutting-edge machine learning inference, like those present in XNNPack or the GPU delegate of TF-Lite. But there's much more complexity beyond the inference, and MediaPipe makes it simple to deal with that. It's a cross-platform framework for ML solutions, combining pipelines of multiple models, inference, GPU acceleration, and synchronization into one easy-to-use package. Speaking about synchronization, there's an inherent latency that stems from the ML inference as well as the camera pipeline, and it adds up to something like 100 to 200 milliseconds, like you can see here on the right. And MediaPipe makes it simple for developers and researchers to deal with that. In the first half of today's talk, I will be showcasing 5 proven ML solutions for live perception. That is face meshes, hand skeletons, human pose, 2D box tracking, and 3D object detection. And in the second half of the talk, we'll be touching base on the infrastructure to enable them. Let's start with the ML solutions. As I mentioned, there are 5 core recipes that we found useful. Number 1, you will see that we're building ML pipelines or small task-specific models versus one big one. And we will be coupling those small models tightly together, and it will allow us to reduce augmentations between them, giving us more capacity for accurate predictions. Because of our limited capacity on mobile, we'll also reduce output layers. And so we favor regression over heat map approaches. We'll also use data sets that have very high quality, consistent annotations, and that will allow us to actually use data set sizes of just like 30 to 50,000 samples. And then we make heavy use of synthetic data to unlock 3D prediction without using any form of scanning equipment. Let's start with our first ML solution, face meshes. MediaPipe FaceMesh is Google's mobile face mesh, driving important first-party applications like YouTube Stories, AR Ads, and Google Duo, as well as third-party developer APIs like MLKit and AR Core. Estimating the high-fidelity human face geometry without dedicated hardware like a depth sensor is an inherent difficult problem. And because of the sheer amount of points that we're estimating, over 480, classical approaches like heat maps just don't scale to so many output layers. In addition to performance, accuracy also matters to drive vital use cases like AR makeup, where we need high-fidelity lip and eye tracking. MediaPipe FaceMesh is accelerated for mobile GPU and mobile CPU and is available to developers in MediaPipe, TFJS, MLKit, and AR Core. Let's look at some of the applications that I just mentioned. You can see we're driving virtual makeup and self-expression effects in AR ads, selfie effects in Google Duo, as well as in YouTube Stories. So how's it work? Our FaceMesh is implemented as a MediaPipe pipeline consisting of two models. The first one is a BlazeFace face detector that locates the face in the image and returns an oriented region of interest. And then the 3D FaceMesh that operates on this region of interest and predicts the 486 landmarks. The nice thing about implementing it as a MediaPipe pipeline is that we actually don't have to run the face detector on every frame, but only on the first frame or if there's a tracking error. Otherwise, the FaceMesh can reuse the region of interest derived from the previous frame. So as I said, in some frames, we need to run two models. So our face detector needs to be fast, indeed, blazingly fast. BlazeFace computes some landmarks that yield an oriented region of interest for the FaceMesh and is optimized for selfie use cases on mobile phones. When compared to a state-of-the-art face detector, you can see that BlazeFace is just as accurate, but roughly 4 times faster. BlazeFace is accelerated on mobile GPU and CPU, as well as available on web. It is available to developers in MediaPipe and TF.js, and developers' responses have been really positive, telling us that it is performing better than what is available by default on iOS. You can also have a look at our model card that will give you the performance metrics across different regions of the Earth. Now let's have a look at the FaceMesh. Our FaceMesh predicts 486 3D landmarks from the region of interest determined from BlazeFace. We also couple our model quite tightly to this detector. For example, we limit offset augmentations, having more capacity for high quality predictions, as well as predict when the detector should be triggered again. Now, one interesting bit about the FaceMesh is the data sets that it has been trained on, where there are 3 of them. The reason is that annotating high-fidelity landmarks from scratch is extremely difficult. And so instead, we followed a bootstrap approach. We took some synthetic data as well as 2D landmarks to train an initial model. And that initial model then was used to bootstrap annotations on raw face images and refine them with human in the loops to yield ground-truth annotated data that we then use to retrain our model. And we run this loop a couple times to yield our final production model. Let's have a look at those annotations. Here you can see a recording of annotators moving sets of landmarks and key regions such that they are correctly aligned with the underlying image. It takes about 5 minutes per image. One interesting question is, how good are humans at this task? And so we gave the same image to be annotated to several humans, and we measured the discrepancy. And that is roughly 2.5% of the interocular distance, meaning the distance between the pupils of a human. So fairly small. Here you can see that our model actually achieves roughly human performance measured across different regions of the Earth. Our performance is between 2.4 to 3.5% ILD. And we also train a variety of models. Some are larger in capacity, some are smaller in capacity, and they vary with respect to performance as well as inference time. Let's have a look at the ML fairness evaluation that we are performing. To do that, we're grouping the regions of the Earth into 7 geo-regions as defined by the United Nations. And we ensure that our test set has equal representation across those regions. We consider a model to performing unfairly if the error range across those regions is larger than the human annotation discrepancy, which is 2.5% IOD. And you can see for our full FaceMesh, the discrepancy between regions is roughly 1%, so quite a bit less than the human discrepancy. And for details, please have a look at our model cards. Now, let's look at some of the applications of the FaceMesh. Our first application is highly realistic AR makeup via image filtering. For that, we use the FaceMesh to obtain an accurate lib region of the user, and then we divide the light spectrum into several ranges, filter each range individually, apply the virtual makeup, and then we blend it back together with the original image. And when evaluated by users, roughly half consider our rendered AR images to be real. Our second application is MediaPipe Iris, which extends the FaceMesh with 5 landmarks per eye, and it's a separate model that is run after the FaceMesh. Now, with MediaPipe Iris, we're able to estimate single image metric depth. And here we leverage the fact that the iris diameter of humans is roughly constant at 11.7 millimeter. And so if you have a known metric focal length, for example, you can obtain that from the EXIF data or any capture API, we're able to show that we can determine metric depth within an error of just roughly 5%. What you can see here on the right, when you compare the ruler markers with the depth as determined on the mobile application. Our last application is Puppets in Duo, which is using the FaceMesh and Iris models combined to derive continuous semantics capturing the facial expressions of the user. And then we can use that to drive Puppets in Duo on iOS and Android, as you can see here in the top right. The second ML solution we're going to look at are hand skeletons available in MediaPipe and TFJS. Hand tracking is a uniquely difficult problem. That's because hand sizes occur in all kinds of scales, from very close to the camera to far away. They tend to be highly occluded, for example, with face or the body, and also among them, imagine a hand from the side where the fingers occlude each other. They come in a myriad of poses and gestures, very deformable, and they lack the contrast that you usually have when you do face or people tracking. However, once you solve it, there are a variety of very interesting applications. The way we built MediaPipe hands is again as a MediaPipe pipeline consisting of 2 models: a palm detector that returns an oriented region of interest that we then crop, and then a landmark model that operates on that crop to predict the key points. Again, we have the advantage that the palm detector doesn't need to be run on every frame, but only on the first frame, or if the landmark model indicates that it should be triggered again. Now, one interesting design point that we did is instead of hands, we do palm detection. Why is that? Number one, palms are rigid. So you don't have any articulated fingers, they just don't deform as much. They're also fairly small. If you have 2 hands interlocked, you still can tell them apart with non-max suppression. And they also have a roughly square aspect ratio, so you actually only need very few anchors. And otherwise, we follow a similar design to BlazeFace, where we output anchors as well as 7 landmarks per palm to localize the region of interest. However, there are some interesting additional design choices. We adopted building blocks from recent literature. The first one is a feature pyramid approach. So instead of just predicting anchors at the smallest resolution with the highest semantic information, we also upsample again and then predict at each of those resolutions. That helps us to localize smaller hands. And then hands tend to be fairly sparse with respect to the background. And so we use a focal loss from RetinaNet to address this foreground-background imbalance. And if you combine both these approaches, you see that in our ablation study, you get a sizable improvement or boost in average precision. The landmark model operates on the region of interest from BlazePalm and then predicts 21 3D landmarks. And again, we trained it on 2 data sets, real world as well as synthetic. For the real world data set, we simply annotated 21 key points with humans on roughly 100,000 images. This is a simpler task as for face meshes, just because the number of points are much smaller. And you can see some of the ground truth examples at the bottom. When you ask the question, how good are humans? There are differing with respect to the palm height of roughly 4%. Here you see the 3D synthetic data that we use. With a blend shape model, we rendered roughly 100,000 images with accurate lighting to make it realistic, and we composited them onto backgrounds, and then we mapped this 3D model to the same 21 key points so we can jointly train it with the real-world data. If you combine real-world and synthetic data, you can see here you get a sizable quality boost. So from 16% error down to 13.4% error. And the synthetic data also helps us to unlock 3D prediction because it's the only one that can provide us with a Z coordinate. And you see this in the example over here. Bright is closer to the camera, dark is further away from the camera. One interesting application of hand tracking is gesture recognition. And using landmarks has the advantage it scales to hundreds of gestures. So you don't need a separate network for each gesture, as you can see here on the right, where we simply use the heuristic of whether your finger is bent or not. MediaPipe Hands comes also with a model card, and we encourage you to check it out. Moving on to our third ML solution for human pose estimation. MediaPipe BlazePose was recently released, and it aims to provide beyond state-of-the-art quality and real-time speeds. Now, one of the key challenges of human pose estimation is that the default key point topology actually only localizes wrist and ankle points, and so it lacks the hand and the foot location. And that makes it ill-suited for interesting use cases like fitness, yoga, or sign language recognition. BlazePose runs in real time on mobile as well as on web, and it focuses on tracking few people relatively close to the camera. Let's have a look at the key point topology. It's a new 33 key point topology that localizes feet as well as hands, and it's a superset of the 17 key point Coco pose and then the BlazeFace and BlazePalm architectures that I showed earlier. Similar to our other pipelines, it consists of a detector and then a landmark estimation model. Here we extend BlazeFace such that it returns two additional virtual key points, one that denotes the middle or center of a human, and another point that describes radius as well as orientation. The landmark model then predicts 33 key points with a per point visibility. Are you inside the image or are you not? And also these two virtual landmarks to derive the crop for the next frame so that we don't need to run the pose detector on every frame as earlier. One interesting design principle behind the landmark model is that it's not just a regression network, but it's a regression with heat map supervision. So what we actually do is we first train column A and column B with heat maps that we derive from ground truth annotation. Then we remove the heat map head, and then we only predict the tower C that yields 33 key points and the visibility. When you look at the performance, you see that BlazePose on challenging datasets like yoga performs similar to the state-of-the-art open pose, but is significantly faster. There's some interesting applications for BlazePose. Number one, it's powering the new MLKit Pose API, and you can use it to count fitness repetitions by simply matching the 2D key point distance to a target pose. And here you can see our most recent performance numbers using CPU and GPU acceleration. Our fourth solution is 2D box tracking, which is a general purpose tracking to track any target via a two-stage process. First, we run motion analysis from sparse optical flow computation on a frame. Then we classify the features into foreground and background, as you can see here with red and green. And then we derive tracking metadata. The actual tracking is then done on the metadata, not on the input image anymore. And that allows us to track multiple objects with minimal latency. Our first rollout was in Motion Stills 2018 for moving stickers. And since then, we launched it in Lens for gleaming and text highlighting, as well as for real-time translation in Lens as well as in Google Translate. Box tracking is also available in MediaPipe, where it's bundled with on-device object detection. You can follow the webpage here to check it out. Last solution that we're going to look at is 3D object detection. We call this MediaPipe Objectron, and it aims to compute 3D bounding boxes for whole categories of objects like shoes and furniture versus a particular instance. And not only does it determine the 6th pose from the image, that is the rotation and the translation, but also its 3 dimensions. It's released in MediaPipe, and it performs in real time on mobile devices. Now, the interesting question here was, how do we get the actual ground truth data? And the key observation was that frameworks like ARKit and ARCore are providing you with some form of sparse, self-driving point clouds, plane geometry, and camera poses. And so we wrote a capture application to collect roughly 16,000 videos, and then an annotation tool where basically annotators simply annotate a single frame with a cuboid. And because we have the 6th ground truth camera pose across the whole video, we can then propagate it to all the adjacent frames. It's a very efficient way to annotate a video sequence with many, many objects. The actual model is a multitask model that predicts the center of an object as a heat map, and then it predicts 8 offset maps for the 8 individual corners of a bounding box with an optional segmentation mask for handling occlusions. You can see that visualized on this slide. So you can see the heat map with the offsets, as well as the segmentation mask that you can use for handling occlusions. Objectron is available in MediaPipe for the categories of chairs and shoes, and it performs really well in real time on recent mobile phones. In the second half of this talk, we'll be looking at infrastructure for live perception, starting with MediaPipe. MediaPipe aims to make cross-platform ML solutions simple for researchers and developers to build across mobile, edge, cloud, and the web. And it's widely used across Google in research and product to build ML solutions. It provides end-to-end acceleration, not just for the inference, but also pre, post-processing, and rendering to use CPU and GPU. It's cross-platform, as I mentioned, comes with a variety of ready-to-use solutions. A lot of those we looked at in the first half of the talk, and it's free and open source. Looking at the acceleration, it integrates with TensorFlow Lite and can take advantage of CPU, GPU, as well as edge TPUs. And here you can see how it reflects in the speed on a mobile phone. FaceMesh is roughly twice faster using end-to-end GPU acceleration. Segmentation even 6 times faster using end-to-end acceleration. And it comes with a variety of pre- and post-processing GPU building blocks. Here you can see an example of cross-compiled ML solutions. This is a Google Motion Photos on the left running on Android, and on the right running in Google Photos in your web browser. It comes with a variety of ready-to-use solutions. Most of them can run across all these platforms, and we touch base on a lot of them. And as I mentioned, MediaPipe is free and open source. It comes with an Apache 2 license. You can use it to build your own ML solutions, or use the existing ones, or customize them even further. Let's look at an example of what is actually happening under the hood to build a solution like the hand tracking one, which is much more than just running the inference. Usually, a simple machine learning pipeline consists of a variety of building blocks, as you can see here. We start with the input video. Usually, we do some kind of color conversion or resizing and cropping. Then we have to convert it to a tensor, run the actual inference. If it's a regression network, we get the landmarks out, and then we usually want to render that at the minimum with the input image before we present it, the video on display. All of this is abstracted in a MediaPipe pipeline We call this also a MediaPipe graph. Each of these nodes we call calculators, and calculators are connected with a stream where packets are flowing from the output of one calculator to the input of another calculator. MediaPipe comes with a variety of built-in calculators for image and media processing. It also comes with calculators to make inference very easy, leveraging TensorFlow and TensorFlow-Lite, and then has a variety of post-processing calculators for common machine learning tasks, as well as utility calculators, for example, for annotation, rendering, or flow control. One really nice bit of MediaPipe is that it makes synchronization very simple. By default, all the inputs to a calculator are synchronized, and so the frameworks does the heavy lifting to time align, for example, machine learning results with the input image, so you have a synchronous rendered result that you can present to the user. Here's an example of the hand pipeline that we have been looking at earlier. As you can see, everything is done on the GPU end-to-end from the input to the output, ML inference as well as rendering. You can see the two models, landmarks and hand detection, working together across frames. And the results or the details are actually fairly involved, so I encourage you to check out the details on our visualizer link. Second building block is accelerating on-device ML inference. On-device inference is fairly challenging because mobile CPUs tend to be much less powerful than server CPUs, and inference by itself is costly, so we're adding yet another compute-intensive task to CPUs. We also have limited memory and memory bandwidth, so model size really matters. Smaller models are preferred, and we have to deal with additional costs. For example, increased energy consumption results into shorter battery life for users, and then we have a thermal profile that's more complex, and we have to deal with throttling and ergo slower computation. We'll be looking at two solutions: CPU acceleration via XNNPack and GPU acceleration via the GPU delegate for TF-Lite. Let's start with XNNPack, which is a neural network operator library that provides highly optimized implementations for various floating point operators. They're optimized for ARM Neon as well as x86. And several critical ops, like the common ones, conf, deconf, fully connected, they're further tuned in assembly for ARM cores in mobile phones. XNNPack also provides some operator fusion, so it detects common combinations of ops and fuses them into a single accelerated op. It has been recently released and is now available in TF-Lite, where it provides a roughly 30% to 2x speedup over the former CPU implementation across a variety of models. Some of those we touched base on, and it's currently opt-in for TF-Lite and will be the default for future releases. Second way to provide on-device machine learning acceleration is to leverage the mobile graphics processing unit. The GPU provides 5 times as much compute power compared to the CPU, and that has been consistent across the years. And today, the majority of Android devices support the OpenGL ES 3.1 compute shader standard that we have been leveraging. The GPU acceleration is available in TF-Lite as an optional backend today. One could ask, can't we leverage neural processing units for on-device acceleration as an alternative? And there the challenge is the landscape is still fairly fragmented. And so what you see is it tends to be limited to vendor-specific apps, like the camera apps. Especially low-end phones tend to not have NPUs today. And then there's still no unifying SDK or compute standard available. And so we've been leveraging GPUs. For GPU acceleration, there are two interesting building blocks. The number one is a GPU-friendly tensor representation or memory layout. What we do is we divide the channel dimension into multiples of 4, and we use interleaved storage format for that. So we can use these swizzling techniques for XYZW lookup in our shaders. And then we optimize shaders by itself. Number one, we reduce the number of shader programs by using a lot of fusion of ops into more complex ops. We reduce the memory bandwidth that we need by inlining small tensors into shader programs. And then we specialize shaders in two ways. Number one, for commonly used hyperparameters, like for example, the one-by-one convolution, but also we specialize for particular GPU families like Adreno or Mali or even individual chipsets. We leverage two graphic standards, OpenGL as well as OpenCL. OpenGL is roughly twice faster than the GPU. OpenCL, more recent, we just unveiled this year, is 4 times faster than the CPU, and that speed up is fairly consistent across devices and recent model architectures like MNES-Net or MobileNet v3. That concludes our talk, so it's time for Q&A.